Hello, this is Chuma-Okere from the group 3110Dodos, and this video covers statistical analysis using different tests. Before performing any statistical analysis, it is important to characterize your data. This will determine what statistical test you will perform. We will limit our discussion to continuous data because this is the data type most frequently encountered in biomedical engineering. The most common statistical tests for effect on the mean value of a response variable. We will now explain several tests to do this. The first test we will look at is an unpaired t-test. The following data set was used for the paired t-test and the unpaired t-test, where one experimental group was compared to a control group. T-tests can be classified as one or two-tailed, describing the different rejection regions used for each test. If directionality can be assumed, for example, a study examining heart rate before and after exercise could assume that heart rate increases during exercise. A one-tailed t-test is used. If the directionality of response is unknown, a more conservative two-tailed t-test must be used. The p-value from a one-tailed t-test is exactly half the p-value from a two-tailed t-test because of the additional assumption of directionality. The plot shown here is representative of an unpaired t-test. Bars represent mean response values and error bars represent standard deviation. Here, we use the MATLAB function t-test2 to run a two-tailed unpaired t-test, which produced a p-value of 6.6215 times 10 to the negative fifth. If the control and experimental conditions are conducted on the same sample group or group of subjects, a paired t-test is used. An example where this would be relevant is a study examining the efficiency of a manufacturing process under two different conditions. This test compares each subject's response under the experimental condition to the response under the control condition. If the experimental condition has an effect on mean response, the mean, which is the experimental response minus control response, will not equal 0. The plot here is representative of a paired t-test. The bar represents mean, which again is experimental response minus control response, and error bars represent standard deviation. This better represents the comparison made by a paired t-test than plotting mean response values for the control and experimental group side by side as done for an unpaired t-test. Here we use the MATLAB function t-test to run a paired t-test, producing a p-value and h-value, with the h-value indicating that we can reject our null hypothesis at a 5% significance level. Analysis of variance, otherwise known as ANOVA, tests for differences in means of two or more groups. This test is useful if more than one experimental condition is tested. The test result indicates whether any of the means is different from the rest. To determine which mean is different, post hoc pairwise comparisons must be made. The following dataset was used for ANOVA, Kruskal-Wallis, and Laverne's test, which will be shown later in the video. The plot shown here is representative of one-way ANOVA. Bars represent mean response values, and error bars represent standard deviation. The MATLAB code ANOVA1 produced a p-value, graphs of box plots, and an ANOVA table. All of the previous tests are parametric statistical tests. Statistical tests can be classified as parametric or non-parametric. Parametric tests are most commonly used because they have high power, which means they are less likely to incorrectly reject the null hypothesis, but make more assumptions about the data. Parametric tests assume that the samples are independent, that the data are normally distributed, and that the samples have equal variances. If these assumptions are violated, non-parametric tests must be used. Non-parametric tests are often used if sample size is low, which means that they invalidate the assumption of normal distribution, or if the data is better characterized by median than by mean. The Mann-Whitney U-test is the non-parametric counterpart of a t-test. It tests for difference in median response value between two experimental groups. The plot here is representative of the U-test. Because the test does not compare means, the bars represent median response values and the error bars represent interquartile ranges. In MATLAB, a Wilcoxon rank sum test is used since it is equivalent to a Mann-Whitney U-test. The rank sum code produces a p-value and an h-value that states we can reject the null hypothesis. The Kruskal-Wallis test is the non-parametric counterpart of the ANOVA. It tests for differences in median response value between two or more experimental groups. The plot shown here is representative of the Kruskal-Wallis test. Because the test does not compare means, the bars represent median response values and the error bars represent interquartile ranges. The code Kruskal-Wallis returns a p-value, ANOVA table, Kruskal-Wallis statistics, and box plots of the data. All of the tests previously described compare central tendency, that is, means and medians, between data sets. It may also be valuable to compare dispersion or variance. This will be important if comparing the precision of different testing equipment for quality control. It also may be done before statistical analysis in order to validate or invalidate the parametric assumption of equivariances, also known as homoscedasticity. There are several tests that compare variances, including the Fmax test, Bartlett's test, and Levene's test. The Fmax test compares variances between two samples, whereas Bartlett's test and Levene's test both compare variance between two or more samples. The Fmax test and Bartlett's test are both sensitive to violation of the assumption of normally distributed data. Therefore, we will show an example of Levene's test here. The plot shown here is representative of Levene's test for equivariances. Confidence intervals for standard deviation are shown, where non-overlapping confidence intervals indicate statistical significance. The MATLAB code for Levene's test generated box plots of the value, a p-value, f-stat, and degrees of freedom. That concludes this statistics video. Thank you for watching and have a great day.